Okay, so we'll start. All right. So previous few lectures, the first 2 weeks, we have talked about what is the language to measure time complexity of an algorithm, and also look at some examples given the input algorithm to analyze its time complexity. Okay, so from today onwards, we're going to start to look at the given a problem, what are the ways to design efficient algorithm as well as then to analyze them. Okay. In particular, today we're going to start with a simple example. We're going to look at the search problem in a sorted array. Okay, and then we use this also as a way to lead to the concept of recurrence and also how to solve recurrence to obtain the time complexity. Okay, and the recurrences come very naturally when we have a recursive algorithm. We'll see the example very soon. Okay, all right. So let me start with why do we even care about this problem? Okay, some motivations. Okay. Now we already talked about the general search problem. So in the simplest form, you're given an arbitrary array of n numbers, okay, stored in A, and you're also given a target key K, and you're supposed to find out whether the array A contains this key or not. Okay. Now we also said last time that for this general search problem, if you know nothing about this array of numbers, okay, then you have this big omega of n theoretical lower bound, which is tight because in the worst case, you have to check every element in the array in order to know whether your key K is inside or not. Okay, and the linear search procedure achieve an optimal running time, which matches this theoretical lower bound. Okay. But the question is that can we do better? Okay, especially that suppose we're going to have a lot of this kind of search queries. We're going to have to perform this query, the search problem again. Okay, can we somehow make this more efficient? Okay, now the idea is that what if we make the input array to have some special property? Let's say that if this is already sorted, it turned out that indeed we can do better, but of course there's a small price to pay. Okay. In particular, before I get to that, so here's a more real example of why we care about the search. Okay, in general, large data sets are often stored in some databases, and there are different ways. Each of the entry inside, for example, here is for students, the ID, the name, and the level, the year in the university. And in general, they are indexed by some key. That's how they are indexed in the database. And you can perform a query, for example, what is the name of the student with PID, the 8172, okay? And if you think about it, okay, given the same database, okay, the database is there, we often expect that we're going to make a lot of queries. Okay, someone else may come to query another student, maybe query which year they are in, and so on. Okay, or someone may come to say that what is the maximum of any student employee in salary, or someone says that return me all the students whose last name has starting with letter from B to H. Okay, so this is something. The last example I'll give you is something called the range query. Okay, so you can either search for a specific entity or you can perform a range search. You want to return a whole bunch of records, satisfy some condition. Okay, so this is very common and ubiquitous in practice. We constantly use perform database searches without necessarily even realizing that. Okay, and now given that this kind of complex queries are going to be asked many times. Okay, any user can come and then issue a query to the database. So it makes sense to organize the data in a way, okay, so that they can support these queries more efficiently, okay? And of course that if we're going to do that, okay, then now we have an extra step. Okay, you're given all this data, all the students' information. Okay, you want to first put them in a database and organize them in a form that's easier for later queries. But the time it takes to prepare, organize them in this specific form is called the pre-processing time. Okay, because this is a time you have to do beforehand. So there's an extra cost, pre-processing time. But the goal is that after you preprocess it later, the time to take answering the query is called query time. And the hope is that then the query can be more efficient. Okay, so to reduce the query time. Okay, and very often it makes sense to spend some preprocessing time to organize the data in a better form, as long as if this can significantly reduce the later query time. Okay, especially if there are many queries to be performed. Okay, now just to make this point, let me actually start with a simple example. Okay, so again, let's say that I have a database of size n, and the database is indexed by some key, which is just real value numbers. Okay, and imagine that later I know that I'm going to perform m kind of search queries. So I'm going to check probably for m different keywords, whether they're inside the database or not. Okay, so that's what we're going to have. It's not just a single query. Let's say later we're not going to have m queries. Okay, all right. The first strategy, the brute force strategy, is that we don't do anything. The input data, whether it's stored in the array or whether it's stored in the list, we take it as it is. Okay, so if we do this, the preprocessing time, we don't need to do anything. So you can say that preprocessing is order of constant. Okay, it's order of 1. Okay, I should be more precise. Let's just write the big theta of 1. Okay, but then the price to pay is that the search, since there's no information available, we have to perform linear search. And in the worst case, linear search can take theta of n time. Okay, for each of the query. Okay, and since we have m such query, what is the total time that I need for all of this m such query? Well, that's a preprocessing time plus that m query, each one take a linear time. So altogether, this takes theta of mn time. Okay, so altogether, this takes theta of mn time. So this is the brute force approach. Okay, let's say what if we do a little bit of work beforehand, preprocessing, to make the, and it's just an example, if you're going to issue n queries, so if later you're going to check for order of n number of students, their information, then the total time of this brute force approach, it takes quadratic time. Okay, the total time means that everything, all the time to perform all the queries. Okay, all right. Now, let's now look at the second approach, where in the preprocessing stage, I sort all of the elements in the database based on their key. Okay, now sorting can be done in n log n time, which we're going to cover in the next class. Okay, but sorting can be done in n log n time. Okay, so I have to spend, in contrast before, I don't have to spend any time in preprocessing. Now I have to spend n log n time for preprocessing. Okay, however, what is the benefit? The benefit is that now that your database is already sorted by their keys. To perform a search, we're going to use the binary search in the sorted array, which we're going to talk about today. Okay, and we're going to see that the binary search in the sorted array only takes log n time for each of the query. Okay, and now what is the total time? Well, the total time we need is that I first have to do preprocessing, well, now it's n log n. Then I have m queries, m search problem I have to perform, and each one take log n time. So that's m log n. The total time is m plus m log n. Okay, so again, if in the case where m equal to m, what do I have? Then the total time in this case is big theta of m plus n log n, which is 2n log n, which is still the order of n log n. Okay, so what did we say? We say that before, in the brute force approach, you don't have to do any work beforehand. There's no preprocessing, okay? So, but then the total time after n queries is quadratic. Now, in this new strategy, I have to do a little bit of work at the beginning, okay? But then I get the data into a form, which is really easy for later processing. So now when the query comes, I can do that efficiently. The total time after n queries is only n log n. Okay, so clearly this second strategy is much smaller than this. In general, the second strategy well pays off if, as long as the number of queries you have is bigger than log n, then the second strategy start to pay off. Okay, in practice, we typically expect that once you have a database, we may have to have a lot of queries over that. Okay, that's why you want to spend a bit of pre-processing time. Okay, now this also shows that in this case, okay, there's a need for us to now to do a search in the already well-organized database, in this case, a sorted array. Okay, so binary search and sorted array, this is one motivation. It becomes very common in practice. Okay, all right, as I just said, in general, if there are many queries, if you have to perform certain type of task many times, okay, then very often performing a pre-processing pays off if that makes answering this query later much more efficient. Okay, furthermore, also many times, okay, the query that you have to do is actually has to be done online. So you have the database there, a user comes in and says that I want to search for search for the student quickly, okay? Now this, you have to return the results quickly online, while the pre-processing can be done offline. You can do this before any user, before you put all this database on available to the general public, okay? So that means that even if you don't have too many queries, because we have to answer those queries online, it still pays off to do the pre-processing, to spend some time to do pre-processing if that can support faster online queries later. Okay. All right. So let me, in fact, all right, so now let's talk about the binary search in the sorted array. Okay, we just talked about the motivation. Now imagine that you're in a game show. You have n doors given to you, and behind each door there's a number. Okay, now opening the ice door is equivalent to access the ice element in your array A. Okay, and you're supposed to guess which behind which door is the number 42. Okay. And now with every wrong guess, your reward money will be reduced, which means that in order for you to make make some prize money, you want to be able to identify where 42 is as quickly as possible. Okay. Now, if there's no structure behind all this, if the numbers can be arbitrarily placed behind the doors, okay, as we said earlier, you cannot do better than linear search, because if you open an arbitrary door, let's say that you first open the door which contains 14, you still don't really have an in fact, let's use a different example. Let's say that you first open the door you open the third door and the number is 101, you still don't have any idea where could 42 be. Okay, so this that's why you have to, in the worst case, you have to perform linear search. You have to check every door. Okay, you can just do it from beginning one by one, make no difference in the worst case. Okay, but if I now tell you that this input, the numbers behind these doors are sorted in non-decreasing order, what does that mean? That means that they only increasing or okay, so the numbers from the first element in the array to the last has to increasing or this. Now, of course, you can also sort it in decreasing order, but in this class, when I say sorted, very often I mean that in increasing order, in non-decreasing order. Okay, so if you have this prior information, this extra bit of information, now let's say that if I open the door, the fourth door, let's say I just open it, okay? And I see that, oh, it's 22 here. Now, since you know that the numbers are sorted, where can 42 be? Well, you know 42 is bigger than 22. That must mean that 42 can only be to the right of 22, okay? So in other words, by looking at this door, now I know that, okay, these are all bad. 42 cannot be there. I already eliminate a bunch of bad possible doors. Now I know that 42 can only be to the right, okay? And let's say the next, you again check this door and then it's 84, then you know, aha, then I know this is bad because 42 is not bigger than 84. So then 42 has to be to the right. Now I have only one choice and I identified 42. You only 3 steps instead of, in general, if I do linear search, in this case, I have to use 5 steps instead. Okay, so this is basically the idea why pre-sorting the array help with this search and how it helps. Okay, all right. In fact, we just described the strategy already, but let's think that in general, okay, if you have n doors here, okay, which door should I open first? Okay. Well, we already saw if I open a door and I look at the number there, right? I know that either I found the target I'm looking for already, or if it's bigger than the target, then I go to the right. If it's smaller than the target, I go to the left. Okay, so in either case, I would either remove the left portion or I remove the left portion. Okay, in order for me to remove the maximum possible one, I should pick the middle door. Okay, so in this case, I should pick the 4th door. Why? In this case, I either remove the left, which has half, and the right, which also has half. So I can guarantee that I'm going to remove half of the doors, eliminated their the need to check them. Okay. You may say that, oh, what if I don't pick the middle one? What if I pick, say, the first one? In this case, if my number is smaller than the first one, maybe let's use the second one. So if I pick the second one, and if my number is smaller than the one in the second one, we only need to check, we can remove everything, n-2 number of doors to the right, and only need to check 1 now. Isn't that better? Well, the question is that when you're given the key to search, you don't know which side it's going to fall on, okay? So you have to say that in the worst case, you want to eliminate as many doors as possible. And the best choice for that is that you pick the middle one. So in the worst case, whichever side, left or right, the number you're looking for is going to fall in, you're going to eliminate half of the doors, okay? All right, so we first, the strategy is that we first pick the middle door, okay? And once we look at the middle door, depends on the key you're looking for, you ask, is the number here equal to my key? If it equals, we're done, we're lucky, okay? If not, you say, is it bigger or not? If it's bigger than 22, that means that now I eliminate the left half and only go to the right. But if it's smaller than 22, then I go to, if smaller than 22, then I can, so if the key is smaller than 22, then we can eliminate everybody to the right. We only go to the left, okay? And then in this case, we're looking for 42, it's bigger than 22, so we go to the right. And then as we described earlier, the next step, I perform the same. So now we're already only in this portion. Okay, I already know 42, since it's bigger than 22, has to be to the right of 22. Now we again say which door to pick. I pick the middle of the remainder ones, the remaining doors, okay? And then I continue till I find the 42. Okay, so this is the algorithm that we had. All right, the idea is rather simple. Every time, you basically pick the middle door of the remainder elements, you know where the key you're looking for is going to be in, okay? And then depends on whether the key is bigger than the value behind that door or not, you decide whether you go left or go right, okay? Okay, and that's a summary of the strategy we have. So you pick the middle door, and then this can allow you to rule out half of the other doors, and then you pick door of the middle of what remains, and you repeat, okay? You can continue till you find it. So how do we convert this strategy to an algorithm? Okay, all right. So this naturally gives rise to the following algorithm. So the more precise the problem now is that we're given a sorted array. It's important. Our input is a sorted array by sorted in non-decreasing order, okay? And we're also given a target key T, a target that we want to look. We want to return the index of A whose element equal to T if we find it, if it's in A, or we return none otherwise. Okay, so that's what we want to do. All right, the strategy we said earlier give us the following one. Okay, so here's the pseudocode for what we just described. We have an input array A and the target that we're looking for. Now, the difference is that now I'm also having a start and a stop index. Why? Remember that when we give the earlier example, okay, at the beginning, we pick the middle one. So you're given an array. Let's say the size is from 0 to m, the index is from 0 to m-1, okay? The strategy we described is that the first time I'm picking the middle one, no problem, okay? But later I'm going to recurse on only a portion of the array, okay? It's not the full. I'm going to now perform the same strategy only on a subproblem, on a portion of the array, okay? So, and this portion that I need to check getting smaller and smaller, okay? So this start and the stop is representing what is the portion of the array you are looking for your target, okay? So that's what this says. So given the array T and the subportion of this, so we have, this is array A, and we're given a start index and also an end index. And our goal is to search for the T, is T lies within this portion. Okay, that's what we need to, what this code is doing. Okay, you'll see in a minute why this is convenient to write it this way. Okay, all right. Now, remember our strategy. We're given this portion array that we want to search for the element. Which key do we search first? Which position do we check first? We said earlier that we're going to look for the middle of this portion. So we're going to look for the middle of this subarray we're looking for, okay? Now, given the index start and end, what is the middle index? Well, the middle index is simply that start plus stop divided by 2, and then I'm also taking the floor of it just to make it into an integer, okay? So the middle index for the middle is basically the start index plus end index divided by 2, and I'm taking the floor of it to make it into integer. That's it, okay? So given this portion of the subarray that we're going to check for the target T, I first check the middle one, okay? So that's what we have in the code. We first compute the middle index, okay? Now, if we're lucky, if what elements stored here is exactly the target that we're looking for, great, we found it. We simply return this index, okay? If not, we check, is the element stored here bigger than T? If that's the case, what does it mean? That means that I have to go to the left portion of this, okay? Because if T is smaller than what's written here, what's stored here, that means I have to go to the left, okay? And what does it mean? That means that now I only need to check where is T in this new smaller subarray, which is only this portion. Okay, the left part of this previous subarray. And what's the index for that? That's basically starting from start to middle. Okay, that's what the portion we check now. Okay, and I can look for this by calling the same function recursively. Say that, okay, if the number I'm looking for is smaller than what's here, then I recursively search for this element in this green portion. Okay, in the green subarray, the left portion of the current one. Otherwise, if the number is bigger, smaller, what I store here is smaller than my target T, that means that what I'm looking for must lies within the right portion, this orange portion. Orange is not very obvious. Let me use this brown maybe. Must be in this portion. Okay, in this case, I recursively call the same function, search for our target T within the portion from the middle till the end, this brown portion. Okay, so that's the algorithm of the recursive part. Okay, but our algorithm has more than that. Okay, what are this? Well, These are basically the termination, the stopping conditions. You cannot keep doing this, right? At some point you have to stop. What we see is that if at some point you are given a subarray, and if the end, this is not, sorry, instead of the end here means really stop in the code, okay? Now, if at any moment you are looking at a subarray where the end is smaller than the start, that's what this is saying. That means that I already searched for my algorithm to a point and my array is empty. That means I couldn't find this. So I simply return none, okay? Or you recurse on a subarray. This means that you are now your problem, every time you call this function again, the array gets smaller and smaller, and then you are going to a subproblem where the array has only size 1. There's only one element in the array. When that happens, I can just check. I can check, is right now this only element in the array equal to t? If yes, you return this index, okay? Otherwise, that means that, again, I went all the way, and if the target t is supposed to be in the array, that's the position it should be, and we couldn't find it, so we return none. So that's the entire algorithm. So these are the termination conditions. And these are the recursive calls to help to break down the problem smaller and smaller. Okay, so that's the pseudocode of what we just described. All right. All right. Okay, let's just go through one example. Okay, let's say that this is the input array we're given, what you see on the slide. Okay, there are 11 elements. Okay, and the target we're looking for in this particular example, let's say it's 21. Okay, now when you run the algorithm, what is the first call you run? Well, I want to look for t in the entire array. That means I call the function at with the starting index to be 0, the first one, and the stop index to be the last one, because you are, in general, you're calling if the array size n, you're calling on start equal to 0 and stop id equal to n-1. You're calling on the entire array. Okay, so that's what you do at the beginning. So we call, in this case, we call this in the entire array. That means that I look for the middle at this point. The middle at this point is start plus end divided by 2, and that's 5. I don't need to do floor because it's 5. That means that I need to first check the array elements in the 5th position, and that happened to also be 5, the value. Okay, so now you say that, okay, is 5 equal to the target I'm searching? No. But the target I'm searching is bigger than 5. That means that now I need to recurse in the right side, because the number I'm looking for is bigger than that. So I know for sure the number I'm looking for is only within the subarray, this portion. So using the algorithm, the next call is binary search AT, but now I'm going from middle plus 1, that's 6, till the last one, which is 10. So that's the next call we have. Okay, then you repeat. You check that what is the middle for this part, which is 6 plus 10 divided by 2, and that's 8. Okay, so the next one we're looking for, the second number we're looking for is the one in the 8th position, that's 33. And it's not the target. So you ask, is t smaller than 33? In this case, it's smaller than 33. So that means that now we have to go to the right portion of this, the left portion of this. Okay, and in this case, the next one we're calling, using the algorithm, is from 6 to the middle, which is 8. That's what our algorithm says. Okay, so that's the next one you call. So now we're in this subarray, you again do the middle, now it's 7. So we check the middle, that's 7. and then happen to be the same as the index that target we're looking for. So we return. Within this call, we return 7. And this call returns here, and this returns here, and then we return 7 to the in the Intel for this algorithm. Okay, that's what happens. Okay, all right. Okay. Now